Hi everyone, it's Peter. Sarah is once more working as our cinematographer. Say hello again, Sarah.
Hello again, Sarah.
In an earlier video, I said I could give you all a deeper dive into this machine behind me, our Western Electric number 3 ESS. And quite a few of you asked, so let's go. But to understand what's going on inside this machine, we really have to take a look at its older siblings, the number 1 and the number 2 ESS first, because knowing about the decisions they made when they designed those machines will help us make sense of the features and quirks that we find in the number 3. While we do have a few full frames of a number 1 ESS in our offsite storage, I'm afraid that putting them on display is a museum project for the distant future. So in this video, I'm going to be showing you some of its interesting component parts, as well as lots of diagrams and pictures of stuff. My main source for this history is Amos Joel, a Bell Labs researcher who wrote a book with the super long title, A History of Engineering and Science in the Bell System, Switching Technology, 1925 to 1975. One of Joel's many projects at Bell Labs was being part of the design team for the 1 ESS. He was just one member of the big team, of course, but he can speak with plenty of authority when it comes to this machine. The other main source I used for this video is the Bell System Technical Journal, or BSTJ, which had many detailed papers, including one entire issue dedicated to the 1E. Quoting the lead paper in the BSTJ from September 1964, switching systems are, in general, complex and not easy to describe. I think Sarah will agree.
Oh, yes.
But we're going to give it a try anyway. So on to the first part of the 1 ESS. Bell Labs took their first steps towards an electronic telephone switch in 1954 with something they called the DIAD, which stood for Drum Information Assembler and Dispatcher. It used a spinning magnetic drum as memory, and while it was rather crude by their later standards, it convinced them that creating an electronic telephone switch was a real possibility, and that with a few more years of R&D, a working product could be brought to market. In April of 1958, they created a new switching engineering division at Bell Labs. Initially, it was located on West Street in Manhattan, but in 1962, it moved to this famous building in Holmdel, New Jersey, which many people know as the location for the Apple TV series Severance. By 1961, the engineers had a working prototype of a fully electronic central office, which they installed on a trial basis in Morris, Illinois. And fortunately for us, they documented it extensively. Many of the things they learned from doing that trial guided the requirements and specifications for the 1 ESS. The basic architecture was carried forward, even though the Morris hardware design, which used cold cathode gas discharge tubes, was mostly abandoned. Completion of the first production 1 ESS took a few more years, but in 1965, the Bell system officially cut over the first 1 ESS machine in Succossuna, New Jersey. Hundreds more followed in the years after. It's probably best to start with the high-level overview of the 1 ESS, and this diagram from the BSTJ does a pretty good job of showing us the major parts. The central control is a computer, or actually a pair of them. We will get to that, but first we're going to take a look inside each of these other boxes, starting at the top with the switching network. One of the most important requirements to come out of Morris was that the production ESS had to work with people's existing telephone sets. In the Morris trial office, they actually replaced everyone's telephones with specially designed new ones because the voltages and currents on a normal POTS telephone line are not especially transistor-friendly, given the transistor types they had at that time. But to make a real production machine viable, they had to figure out a way to do electronic switching for the telephones that their subscribers were already using. Today, of course, you can get a single IC that can handle all of the voltages and currents you need to power an old-school POTS telephone line. But those ICs were still a long way away in 1960. The 1 ESS accomplished the task of connecting to telephones with an advanced form of electromechanical switching network, which was under the control of the computer. The underlying technology that made this network possible was invented in 1958 by Alexander Feiner and his colleagues at Bell Labs, based on something they called the fair-reed switch. To understand the fair-reed, let's start by looking at a regular old reed switch. We'll put this one under the microscope here. It's just 2 bits of thin steel hermetically sealed in a glass capsule, which protects the contacts from dust and grime. They're pretty reliable and long-lasting. You can see that as I move the magnet close to the glass, the 2 little reeds are attracted to each other and close the circuit. and when I take the magnet away, the circuit opens again. Of course, to make a relay with this, we need to use an electromagnet instead of a permanent magnet to operate the reeds, as I've done here just by wrapping some wire around the glass capsule. When I apply a current through the coil, it creates a magnetic field, the reeds touch, and this little LED that I have hooked up to it lights up. You might wonder why I use two different colors of wire for the coil, and the explanation for that will be coming up in a moment. In the number 5 crossbar, reed switches like this were already being used by the thousands in groups of 5 electromechanical flip-flops that stored the dial digits. That design uses 2 reeds per bit, one to serve as the data and one to serve as a latching element. They are packed inside these steel boxes, which help provide some magnetic isolation. Okay, so now we can talk about the ferrite, which gets its name from some extra ferromagnetic stuff that they added to it. Finer's innovation was to add 2 strips of magnetically remnant material called remendor on the outside of the glass capsule. Those strips become magnetized by the coil, and then they can maintain the field even after the coil is no longer energized. So a ferrite will latch and stay latched without any power needing to be applied. To release the contact closure, they just send current through the coil in the opposite direction to demagnetize the strips again. The final design was a little bit more complicated than that, but this explains the main idea. They experimented with using quite a number of different materials for the strips until they found one with just the right properties, and they finally settled on an alloy of cobalt, iron, and vanadium. Each of these units with a pair of reeds and the remainder strips on the side and the coils around it is called a crosspoint. To see how you connect telephone calls with these, let's look at Finer's highly simplified diagram that shows how 4 crosspoints are used to make a 2x2 array and how you can connect some of those arrays into a little network. Imagine that I want to connect line B to line E. I can set these 3 crosspoints, and now I have a path through the switching fabric. But importantly, that's not the only possible path. Imagine that A was already connected to F like this when I wanted to connect B to E. So part of the path that I showed you before is already in use. But that's no problem. I can still connect B to E by going through the network this way. In this simple little network, I can always connect any of A, B, C, or D to any of E, F, G, or H, and do it all at the same time. But that's not true of real networks and telephone switches, which never provide enough paths for everyone to be using their telephone at once. Of course, many of you will recognize this just as the principle of the crossbar switch, so that part of the plan was not really new. While the number 5 crossbar uses arrays that are either 10 by 10 or 10 by 20, for the 1 ESS they made the network with the basic building block of 8 by 8 reeds like this one. Of course, 8 by 8 makes sense when you're controlling it all with a binary computer. While you can think of the number 5 crossbar switch as a base 10 machine, the 1 ESS was truly base 2. This box was designed to be made in huge quantities almost entirely by machine. If you look closely, you will see that there are 2 coils around each reed which are hidden inside this little tower here. One coil is made of green wire, which connects the rows, and one of orange, which connects the columns. The rows and columns are wound from continuous lengths of wire. And that brings us to another nice feature of the design, which is that it also helps with address decoding. If you know how old-fashioned core memory for mainframe computers works, this is pretty much the same idea. Current going through just one or the other of the 2 coils is not enough to flip the magnetic state of the remendor and close the reed contacts. It requires current going through both coils in order to close the contacts. That means they didn't need to provide separate drivers for each single crosspoint. They could wire all of the rows of reeds in series, and likewise all of the columns, and then just use row drivers and column drivers to select a particular crosspoint. Only the reed at the intersection where both the row wire and the column wire are energized will operate. Let's look at my sample reed on the bench again, and now we see why I also use 2 wire colors. I split the coil, so energizing either half of it alone won't make the reed operate, as you see here. But sending current through both of the half coils does close the contacts, and the light comes on. So when the central computer wants to close a crosspoint, it just needs to send a row and a column number to the network, which puts pulses on the 2 wires to operate that crosspoint. Because of the clever way they did this, The row pulse also releases any other reads in that particular row that happen to be closed, and likewise for the column pulse. I guess I should say that there are actually two little reads in the tower here because the network has to make a two-wire connection. You can see that there are two connections at the top of the tower if you look closely. They did that because you don't want to share a common return path between all of the phones, which would cause a lot of annoying crosstalk and interference, which the subscribers would then complain about. But for simplicity, we almost always show a two-wire connection as just one line in a drawing. One last advantage of these reed switches is that they are not really dependent on being in a nice temperature-controlled environment, and that greatly simplified the cooling story for the entire machine. That's the basic explanation of the 1ESS switching fabric, or the network as they called it. Let's move on to the next box in the diagram, which is called the scanner. Any electromechanical telephone switch, be it a step-by-step switch like this one, or panel, or crossbar, or something else, always has a line relay per subscriber line. The line relay is operated by the roughly 20 milliamps of current that flows through the line when you pick up your phone. The contact closures on the line relay inform the rest of the system that your phone has gone off hook, and that triggers a whole sequence of actions that eventually gives you dial tone. Of course, the 1ESS also needs to know when you've picked up your phone, but instead of line relays, the system uses a device called a fair rod, which has no moving parts. Like the fair reed, the fair rod makes clever use of magnetic materials to create an addressable array which the CPU can scan to learn all about the world around it. Now let's look at another diagram from the BSTJ. Here we have a rod made out of a soft ferrite, which is basically a ceramic material with lots of rust in it to give it magnetic properties. They also made so-called hard ferrites, which are good for permanent magnets, but a soft ferrite like they used here can change its magnetic field easily. The interrogate winding on the left is just one turn of wire going through a little hole in the rod. The readout winding on the right is made in the same way, so it's magnetically coupled to the interrogate winding by the ferrite. Basically, it's a little transformer. Sending in a pulse on the left side makes a signal come out on the right over here. But if we put enough DC current through the outer control winding, the ferrite becomes magnetically saturated, and that prevents the interrogate signal from getting coupled to the readout anymore. Magnetic saturation is what happens when a magnetic material, like iron or these special rocks we call ferrites, have a strong enough magnetic field applied to them that they just can't take it anymore. So then the field created by the interrogate pulse has no additional effect. This whole component forms what is called a scan point, and we're going to look at a real one now. Here's a 1ESS Farad scan point from our museum's collection. There are actually two independent scan points here built together into one unit. It spent the last 35 years or so attached to this memorial wall plaque, which is something that we still have a few of brand new in box. I guess US West made more of them than they handed out. But who knows, maybe one of you retirees who watches our YouTube channel has one of these in a box in your attic? Or maybe even still hanging on the wall in your study? If you do, let us know. Anyway, I managed to gently pry one of them off the wood, and I discovered that it still works. But that's not really a surprise, because there's very little that can go wrong with these things. I'm going to hook one up here on my bench so that I can show you exactly what it does. One moment, please.
A few moments later.
Okay, we are back and everything is hooked up. The yellow trace on the oscilloscope shows you a square wave signal from my function generator, which I'm using to drive the scan point's interrogate winding. I'm driving the winding through an amplifier because it wants a pretty high current pulse of 500 milliamps. Channel 2 of the oscilloscope, which is the blue trace, is connected directly to the rod's readout winding. You can see the pulse that comes out in response to the input. The scanner would amplify that pulse and use it to trigger a flip-flop so the central control would ultimately be able to read the bit. Here at the other end of the scan point, my bench supply is connected to the rod's two control windings, which are also wired up in series with this telephone, just like in the diagram we looked at. In fact, here's a schematic of what I have just set up on the bench. I set the current limit on the bench supply to 20 milliamps because that is what a real telephone exchange would typically provide. Now, when I pick up the phone, you see that current flows through the phone and the control windings on the scan point, and the blue output pulse has gone away. When I hang up the phone, the pulse comes back. Off hook, on hook, off hook, on hook. So the scan point's output is just the inverse of the subscriber's hook state. Because there are no moving parts in here, these farads were super reliable and long-lasting compared to the mechanical line relays that we looked at a little while ago. In fact, farads were one of the few parts of the 1ESS that they did not feel any need to provide in duplicate. As with the farad-based switching network, the farads are arranged in a matrix, which makes addressing them a little easier. An address input from the CPU chooses one of the horizontal wires to be connected to a device called the pulsar, which drives the interrogate windings in that row. Then all of the readout windings in the row put a signal onto their vertical wire, or not, depending on the current in the control winding at that particular scan point. The signals from the vertical wires are sent to the output flip-flops down here, and then the central control can read those bits 16 at a time from the output selector. I'm quoting here from the BSTJ. For convenience and reliability, the scanners are provided in 1024-point modules, which are physically located on the network frames. In addition, one or more scanners are provided for diagnostic and miscellaneous scanning functions. And that's an important point. They didn't just use the scanner to find out which subscribers' phones are off hook. It's the main input device for everything the CPU needs to know. There are scan points connected to the various alarm circuits, to equipment test points, to the announcement machine, and to all sorts of other devices. Then it becomes entirely the software's job to process that information. For example, the software will assign a digit receiver to your line when you pick up the phone, or it can sound a gong for an alarm condition. A big percentage of the central control CPU time just went into scanning. The next major block we should look at is the distributor, which is sort of the inverse of the scanner. It decodes addresses and sends output signals from the CPU to various points of the machine. Using more modern terminology, it combines the functions of an address decoder and a bus driver. In a typical desktop PC today, the bus traces might be a few inches long, but a 1ESS is a physically huge machine. So the central control would need to communicate with peripheral devices that could be as far as several hundred feet away. In fact, the maximum length of the data bus was set to 450 feet. The distributor gets a device address from the central control, decodes it, and then sends an enable pulse over a twisted pair of wires to the specific device that the CPU wants to talk to. The device then knows that it should read the data from the data bus. The peripheral device then sends an acknowledgement signal back over the enable pair, and the distributor forwards that signal back to the central control. If the software does not see that acknowledgement, it will try again. And, because everything is duplicated, if that second attempt still didn't work, it could then try talking to some backup peripheral through a different distributor, and also it would trigger the software's diagnostic routines to figure out what hardware had gone bad and to mark it offline and as needing attention. The distributor did all this with a combination of transistor logic where they needed high-speed signaling and a relay tree for lower-speed high-output current signals. So to sum it all up, you can think of the scanner as a way for the central control to learn about the outside world, and the distributor as a way for the central control to act on that data by controlling the switching network and the other peripherals. And the network is a fancy version of the old-style switchboard where you just plug cords into jacks. This just leaves us to talk about the CPU and its two different types of memory. Those are interesting and unusual enough to deserve a description too, so that will be the subject of part 2 of this video. I'm already working on the script for that one, so it should be coming out soon. I hope you thought that was interesting. I really enjoyed doing the research on this one. Trust me, all of this background will be really helpful when I finally get Colin to show us the 3ESS in more detail. By the way, a few of you asked last time, who is Rich Barger? And the answer is, Rich was a museum volunteer, and this was his primary project before we lost him sadly a few years ago. All right, see you all next time.